An electron in a hydrogen atom transition from n equals to 4 to n equals 2 energy level. A. Calculate the energy of the proton emitted during transition. And B. Determine the wavelength of the emitted radiation. Now let's look at the energy levels of a hydrogen atom. So this is an illustration of the energy levels from n equals to 1 to n equals to infinity. And we all know that the higher you go, the greater the energy. And according to Bohr's theory, when an electron occupies a specific energy level, it carries the energy associated with that particular energy level. So if I'm having an electron here, it has a specific amount of energy that any other electron anywhere on this energy is supposed to have. So if this electron is transitioning down to, let's say, this energy level, it must give off some of its energy in order to occupy a lower energy level. And at all times, anytime it is transitioning from a higher energy level to a lower energy level, the energy that is lost in terms of a photon. So this question says that the electron transition from n equals to 4 to n equals to 2. This means that we are going to have a photon release in the form of energy loss when the electron transition from n equals to 4 to n equals to 2. So this tells us that the energy of the photon is equal to the loss in energy during transition. So for a transition from n equals to 4 to n equals to 2, our energy loss or loss in energy will be equal to E4 minus E2. Since the photon energy and the energy loss during transition are the same, I can also say that the photon energy minus E2. So if I'm able to determine the difference in this energy, I have acquired the photon energy. But when you check, in this particular question, the energies are not given. So we are going to calculate our own energy. We are going to calculate E4 and we are going to calculate E2. Then we strike the difference. So let's begin with E4. So according to Bohr's theory, the energies of the orbit En is given by negative 13.6 electron volts, all multiplied by Z squared divided by N squared, where Z is proton number. And what is the proton number here? The question mentioned hydrogen. What is the proton number for hydrogen? Proton number for hydrogen is 1. So if you are substituting 1 here, 1 squared will give us 1. So that is going to give us our En to be equal to negative 13.6 electron volts, all divided by N squared. For N equals to 4, we have E4 to be equal to negative 13.6 electron volts divided by 4 squared, and this is equal to negative 0.85 electron volts. That is our E4. Now for E2, N equals to 2. E2 is equal to negative 13.6 electron volts divided by 2 squared, and this is also equal to negative 3.4 electron volts. So we've mentioned earlier that the energy of the photon is equal to the difference in energy during transition. And now we have the values of the energies. Our E4 is negative 0.85 electron volts minus negative 3.4 electron volts. So let me put all these in square brackets and give them just 1 electron volt, and this is equal to 2.55 electron volts. So this is the energy of the photon in electron volts. Now we are to change this electron volt to joules, and we've been given this relation that 1 electron volt is equal to 1.6 times 10 power negative 19 joules. So we are going to use this relation to convert to electron volt. So since 1 electron volt is equal to 1.6 times 10 power negative 19 joules, then 2.55 electron volt is going to be 2.55 electron volt divided by 1 electron volt times 1.6 times 10 power negative 19 joules. Electron volt will take care of electron volt. Then we have 2.55 times 1.6 times 10 power negative 19, and that gives us 4.08 times 10 power negative 19 joules. Therefore, the energy of the photon is equal to 4.08 times 10 power negative 19 joules. So the next question says we should find the wavelength of the emitted radiation, and the radiation that is emitted is the photon that we calculated its energy. So we are going to look for the wavelength of the emitted radiation. So B, energy of a photon is determined by multiplying Planck's constant with the frequency of the emitted radiation. In this case, we're interested in the wavelength, not the frequency. But we know that frequency is equal to C over lambda. So you can substitute that in place of frequency, and we get the energy to be equal to hc over lambda. The question says we should find wavelength, and our wavelength is lambda. C is the speed of light and h is Planck's constant. So all we need to do is to make lambda the subject. So making lambda the subject, I get lambda to be equal to hc over the energy. I have my Planck's constant in the question. Planck's constant is given, speed of light is given, and I have calculated for the energy. So all I need to do is to substitute these three variables. So the wavelength lambda is going to be equal to my Planck's constant, which is 6.6 times 10 power negative 34 multiplied by the speed of light, all divided by the energy of the emitted radiation, which is, so the wavelength is equal to 4.853 times 10 power negative 7 meters. The unit of wavelength is meters. So this is the wavelength of the emitted radiation. If you like this video and you want to see the rest of the questions, consider liking the video and hit the notification button so that the moment I drop a video, you'll be one of the first to receive it. I wish you all the best in your upcoming exam.